Okay, let us now start with the second topic today, which is the historical background of this particular subject. So once again, let us go into our class note here, and the second topic after introduction, this was the history, which is historical background of the subject. The developments here, once again. Okay, so let us start. This we have already discussed, our syllabus part. So we are going to start from here. Okay. So the development of the subject will be discussing starting from prehistoric age. And then there are some developments in prehistoric age. After that, there is a middle age. We'll go into the further detailings of that. Then comes the development in science, the renaissance in science, you can say. The contribution of these scientists, okay, that we are not going to discuss their contribution individually. Something is written there. And finally, we will come into the developments in modern times, the recent developments, okay, which is in the current century, 2001 onward, and before that there is an immediate past and recent past. Okay. This you can understand from here. So let us starting from prehistoric age. Here, this is the one we find actually from archaeological findings. There are something more. The Stone Age, nothing. In writing is available there. So whatever is available to us is basically this particular pyramid, which we can find in Cairo or at Giza, that place is called. This is the pyramid of Khufu, King Khufu, constructed around 5000 years ago. You understand, this is 2580 before Christ, roughly 5000 years ago. Then there are some other explorations. So such pyramidal structures are available in deep sea as well. So here what is shown is basically an archaeological remains. This is found in the Bay of Cambe. Okay. This is western coast of India, and this place is known as the Vet Daruka. Now there is a city, Daruka, the modern city, and it is called that this Daruka, old Daruka city at the time of Lord Krishna. Now it is under sea. Some archaeological finding is found here by deep sea explorers, and there are lots of other remains of other civilizations in deep sea. They got many pyramidal structures at the coast of Japan, etc. So this shows that in prehistorical time also there were some civilizations not known to us. So whatever is known to us is basically this pyramids of the Egypt, some hieroglyphics, some script which scientists are trying to decipher nowadays. Okay, and then afterwards actually the progress in Egypt. Okay. So at that time, this Egypt is in south of Mediterranean Sea, and in the north of Mediterranean Sea, there is Greece. Okay. So these are parallel developments. Egypt came first, actually, according to the timeline of the archaeological dating. They use some dating to find out the age of those artifacts or structures. There were Greeks, then there were Romans, etc., etc. Okay. And say for Greeks, there are very old scripts like the Homer wrote Iliad and Odyssey. Before that, there were Hesiod, who had a book on philosophy basically. So, and then this Greeks, they overpowered Egypt. Okay. So Alexander invaded Egypt. Alexandria, this is nearby Cairo. It is named after Alexander. And there are Romans who conquered this Greece and obviously this Egypt. There was Carthage at the time also. So Romans conquered everything. And then what happened? This Roman Empire, it took up Christianity as the religion in 3000 AD. That means about 1700 years ago. 300 years after the death of Christ. So now, after that, from that period when Christianity was taken up as the official religion of the kingdom, that means by the Roman Empire, at that time, this is called the Middle Age. You see here, what is Middle Age? Their religion took over the science. So when there is any conflict, whatever the religious people, the priests, they have the final say. This was the ruling by the Roman kings, by Constantine. And at that time, the Rome was the world basically. Their empire was starting from the inland, the west coast of Europe, to the east. It came up to say beyond Turkey, Iraq, Iran, those part was under Roman Empire, and at that time Rome was one of the capital in European side, and in eastern side there was Istanbul. Istanbul was also another capital of the Roman Empire. Okay. So this upper hand of the religion, it continues in the Middle Age. So what does it mean? You see here, this Middle Age is there. So there are not much contribution from scientists in the Middle Age. This is obvious because at that time it was religion which was the superpower. And then came this particular incident of Galileo Galilei in Italy, who did many scientific inventions. You know about the story of that Pisa's tower, the Leaning Tower of Pisa, from where he did an experiment, etc., etc. And before that, there was Renaissance in some form which came from Leonardo da Vinci. Both of them, Leonardo da Vinci and Galileo, they were Italian, okay? But Vinci was basically an architect, although he has contribution in many other areas. In science also, he developed how to measure the area of a land, the paintings, other things. And Leonardo da Vinci has many contributions. You have to see further detailing on Leonardo da Vinci, but whatever, he was not in direct confrontation with the religion. But it is Galileo Galilei who first understand, actually this was understood earlier also, but he pronounced that Earth is not center of the universe. So according to the religion, Earth is the center of the universe. But Galileo Galilei, he pronounced that this is not true. He goes against the religion and he was jailed, all these things. Okay. So then came the confrontation, direct confrontation between religion and science. It started from that time. So then, starting from Galileo Galilei, what we will say, this is the beginning of Renaissance, not in science, but in the form of architecture, painting, etc. Okay? Altogether new views, which is not found in earlier religious time. That was initiated through Leonardo da Vinci. Then Galileo Galilei, he was in direct confrontation, and there is Copernicus, actually this heliocentrism, that means the sun. This is the center of this universe. That observation was made by Copernicus. Okay. And based on that observation and some other theoretical modeling which Galileo Galilei could develop, he opposed religion. And then what happens, you see, René Descartes, okay, this René Descartes was basically a mathematician, but he has many contributions in philosophy. So today we remember Descartes through our coordinate system. It is called Cartesian coordinate system. So that Cartesian comes from this particular René Descartes. This is the origin of Cartesian coordinate system, named after this philosopher and mathematician René Descartes. Okay. So this conflict between religion and science, it was going on for some time, starting from this time, and when these philosophers came, okay, they made a bridge between religion and scientists, religious people and scientists. So what they could establish, what philosophers could establish, is that the domain of religion and the domain of science are altogether different. So what scientists say is not in the domain of religion. What religious people say, that has nothing to do with science. So that could be established by the philosophers. So from that period, this conflict was not there. Because if two people say about two different things, how can there be conflict? Okay. So from that time, basically the development in modern science, it started from that time. So this is basically the historical background. And we know about this Newtonian mechanics or the Newton's laws. This again is basically a book which came from the observations of many earlier scientists. Okay. So that way Newton, what he could do is basically he could formulate some laws. So it is not that these are the inventions of Newton, it was known. Actually, you must be knowing that any scientific invention cannot be attributed to a particular person. It is named after some person, but the thing is, there are a group who has a similar thinking, and from there, the new theory comes up. It is not that if Newton was not there, those laws would not come into existence. It would always come. Some other scientists would have written that. This is true for every scientific invention. But whatever is there has to be a genesis in the Newton's laws. Okay. where from these laws came. So that also you see there is another viewpoint, and you know that this Newton, he was an English mathematician. Okay. And this particular mathematics, it states some laws. These laws are to some extent mechanical laws. Whereas these people, all of these people, they are from the continent. Continent, you understand, it is called the English people, the British. Now also UK does not belong to European Union.
Yes, sir.
So this European Union is the continent. There is no land connection between UK and this continent. So these scientists, they are mostly French at that time, but nowadays that region is divided into the France, then there is the northern part of Italy, there is Switzerland. Okay. So the geographical division, it has also changed. Whatever is the countries at that point of time and whatever the countries we see today, this is not identical. World War II has changed the geographical markings in a big way. So they have their contributions. You have come across to these things of their contributions in various areas of science, in physics and in chemistry as well. But every one of them has a contribution towards the development of the theory of elasticity or theory of solid mechanics, whatever we say, in statics, in dynamics, like the D'Alembert, etc. So now what next? It goes on from there. You see there is a chronological part in it. These are somewhat a chronological seriality is maintained here. And now coming to the modern science, this continuum mechanics actually broke down at that time, at the time of Einstein, that means at the end of 19th century, at the beginning of 20th century, scientists could understand that the continuum mechanics is not the end of the laws of universe. So, science basically tries to establish the laws of the nature. And till the middle of 19th century, that means up to 1850, the idea of the scientist was that this world is a continuous entity. This continuum mechanics is sufficient to explain the universe. The laws of physics can be explained through this continuum mechanics. But that idea fell down towards the end of 19th century. So there are some laws, theories came from Einstein. Again, it is not that it is Einstein who actually invented that thing. There are some other great scientists, so it is named after Einstein. And then there are developments in 20th century, many developments. This is a chronological naming of those scientists. If you are interested, you make a Google search. Okay. The names are given there, their individual contributions you can find out from here. Okay. Now coming to modern science, okay. So what is there? The Feynman, who was there till the end of 20th century. Okay. So Feynman was a great physicist. In your higher secondary also, you might have gone through the textbook by Feynman. He has a book on physics. Okay, it's a very good book on the physics. Anyway, if you have time, you can read the physics book by Friedman. It's a very good reading as well. Okay. Now, so from 2001 onward, okay, let us come now in the domain of solid mechanics. What are the different domains of mechanics that we will be discussing in the next slide? This is only the historical development. Okay. So what we understand from here is, you see, from starting from Newton, this is fundamental physical, applicable in other systems also. Likewise, in electrical systems, there are Maxwell's law. Okay. Some other fundamental laws are there. But gradually with development, these generalized laws, they are becoming particular laws in specific areas. It has to be. This is the growth in science. It happens from here, from general to particular. So what is here is basically historical development in applied mechanics. So what we get from here, you see, starting from 1950s, okay, from 1957, the first award was given to Timoshenko. I have talked about Timoshenko in the earlier discussion. Okay. This is the Timoshenko, whose textbook you have gone through in your undergraduate. Actually, he has many contributions. He was the first who could formulate a solid mechanics problem into a mathematical model. So, before Timoshenko, modeling of a physical problem, that was not well established. So, this is the contribution of Timoshenko. It's a very great contribution. Okay, and that is why Timoshenko is considered as the originator of this area of solid mechanics in this particular stress and deformation analysis or in theory of elasticity. So there is an award. So this award is given by the Institute of Applied Mechanics Division from the ASME, American Society of Mechanical Engineers. So they give this award from 1957. And you understand, say from 1950s, from the, say, about middle of 20th century towards the end of it, and in recent times, starting from 2001, these are the scientists who got that award for their contribution in the area of mechanics. So it is not that only solid mechanics we are talking about, this is the general. So there are many persons from biological science also. Okay. Like this Suresh is from biological area. So out of this there are two Indians as well. This one is Professor Suresh is from Caltech, I think. Okay. And then in the last year it was J.M. Reddy, who has the book on FEM. He's from Texas A&M University. And you will see in your coursework that there are many of these names which will came in different areas, in fracture mechanics, in plasticity theory, etc., etc. So this is the development, okay, historical development through the scientists. Okay, so this is one part. There is another part which I will be talking about is the development of two parallel branches in mechanics. I have already talked about Newton and the scientists in the continent. Those who belong to, say, Switzerland, France, Northern Italy, etc., in that region, in the region of continent, some part of Russia, East Russia, Southeast Russia, that region, even up to Greece and Turkey itself. So this part you will find even today so many great mathematicians. So this area of the world has the largest number of enriched mathematics people there. Even in USA you won't get that many mathematicians that even nowadays they are having. Okay. So what is the difference here? See, this Newtonian mechanics has a parallel development in the continent, came through this Leibniz, Euler, Lagrange, whatever. So what is the basic difference here? The difference is known nowadays by these two terms. One is called Newtonian mechanics, which is named after Newton. And in this area, which is known as the calculus of variations or variational principle, you can say, in which it came Lagrangian mechanics, and the other thing is the Hamiltonian principle. We will see some differences between Lagrangian mechanics and Hamiltonian mechanics afterwards. There are contributions from D'Alembert, everything. So all these things, they have a different root. The thing is, following any method, you will go to a system governing equation. But the basic idea is different. They are coming from two different aspects. In Newtonian mechanics, it is coming from the fundamental laws developed by Newton. So that way there, you are not getting any basis of those laws. You have to take those laws. These are the laws. Okay. So that is one of the limitations there. So it will fail at some point of time. But if you start from a more generalized, say, idea, which even can explain the genesis of these Newtonian laws, you are at a higher level. So that is why nowadays you will see modern times the variational principle, which are basically developed by many scientists, D'Alembert, Lagrange, Hamilton, etc. They have a different idea of developing the system equation. This is okay. Actually, this is in the area of solid mechanics, the way we are talking about. But there is a simile in the area of pure mathematics also. If you go into the solution of system governing equation, this is a mathematical equation in the form of ordinary differential equation or in partial differential equation. So there also the same logic is applicable. Okay. So this should be known to you that there are two major differences in the development of system governing equation. One coming from Newtonian mechanics, the other coming from the energy principles or through some based on a variational principle which comes from calculus of variations. And you know that this calculus was developed parallelly by Newton and by Leibniz at the same time. And actually Leibniz is in some form earlier than Newton in development of calculus theories. But the recognition comes through a writing, through a paper, what is followed nowadays also. You have to publish paper to get yourself established in science. So, but these things are there. So, this is the two branches of development, and what happens then. In Newtonian mechanics, there is equation of motion, but this equation of motion, okay, they are limited in non-inertial frame. Basically, they are applicable for rigid bodies. You see the application area which is coming from Newton, right? You follow that error. Okay. So that limitation can be overcome if you start from one step ahead. That means following variational principle. So in that line there is Hamilton's equation, Hamilton-Jacobi, other parts are there. So that way all these problems, okay, motion in relative frame, which follows some relativistic mechanics that Einstein actually stated first. Okay. Then the continuum of deformable bodies. For those type of problems, this principle based on variational or energy based method is more powerful. This is fine. You see, in your undergraduate studies, you did some problem based on Newtonian mechanics up to the rigid body mechanics.
Yes, sir.
And whenever you have come into solid mechanics, the strength of materials, there you solve some problem following Newtonian mechanics, but when there are some typical problems like bending of a clamped beam, you won't get any direct solution of that particular equation, system moment equation. Right? There is Castigliano's theorem and other theorems, etc. Those are basically energy-based theorems. Those are not force balance equations. So, basic premise of Newtonian mechanics is a force balance condition. Okay? And the basic premise of this variational principle is basically energy conservation. Domain, the basis is energy conservation. So, this principle of energy conservation basically, is much more powerful than this equilibrium of force. Because equilibrium of force is a natural consequence of the conservation of energy. That is what I was talking all through. This part is clear now? Okay. So this is the thing. There are some philosophical background that I was talking about. So the parallel development in energy-based principle, it originated from this particular scientist. It is very difficult to announce his name, whatever I will try to develop that thing. But what is the idea here? You see, all changes that take place in the universe, the sum of products of each body multiplied by the distance moved, and by the speed with which it moves is the least that is possible. This is the same as the conservation principle or the principle of equilibrium, which comes from variational principle. This is the basis from which variational principle developed. So what they thought, basically the behavior of this universe coming from a higher thing, it is not an object, which is not based on force, rather the thought of something from which force is derived. And nowadays we know that it is the potential energy. The derivative of potential energy gives us the force. Okay. So that is why this is the basis for that energy conservation principle nowadays that we know as today, and there are statements of those energy-based principles in our solid mechanics. So this is the development starting from this scientist. Okay. So there are some stationary action, etc. We will be discussing about this thing when we go into variational principle or energy methods. So now what whatever, this is pure physics part, not our domain. And this Feynman he predicted that the fall of quantum mechanics, it came earlier also. Feynman has already predicted that thing. It is not continuum mechanics actually. It has to break down afterwards. Feynman has other contributions in many other branches of physics. So this is something about, we have talked about continuum mechanics and developments in variational formulation, right? So some detailing is there. Let us see. Newtonian mechanics is based on vector quantities, force, momentum, acceleration, and calculus of variation is an alternative approach that is based on identifying the path that minimizes an integral quantity. This integral variation approach was first championed by Leibniz, this contemporary of Newton. So this is the thing you will see in Newton mechanics. They are based on these quantities. There is force, there is momentum, there is acceleration. But these scientists, there are a group of scientists, they thought of something, okay, that minimizes an integral quantity. So this integral quantity encompasses the force, and you can take displacement, velocity, acceleration, whatever.
Magister component of displacement.
Whatever. So ultimately it gives to that energy.
Yes.
And you are conserving something, that this minimization is a conservation principle, right?
Yes, sir.
So you are using that principle of conservation of energy in some form. Then comes these things. The Bernoulli, as a student of developed field of variation. Actually, there is a problem. There is a Brackley-Stone problem. In variational principle, we will be talking about that. There is another problem similar to that. This is known as the problem of if you hang a cable from those, what it is called, catenary. The shape, you know about catenary problem? Okay, catenary is a shape. If you hang a cable from 2 points, that, say, a chain, that chain will take up a particular form. It is a particular form, it is not an arbitrary thing. Okay, you have 2 points, say 10 meters apart, and you have a chain whose length is, say, 12 meters. What will happen if you hang the chain? That chain between the distance of 10 meters, it will take a particular shape. It is not that the 2 end points are in the same horizontal, one their horizontal level can be different. You will get a lot of shapes if you change the height of the end points.
So it is like a geometry problem.
Some sort of that problem. Yeah, the same problem. So these are one of the fundamental problems. The Brackley-Stone problem, the catenary problem, etc. So those were the problems from which the variation in calculus was developed. Another very fundamental problem was the bending profile of a beam. In beam bending with large deformation, what is the profile of that? In that line, so you know that the bending equation of beam is known as Euler-Bernoulli beam equation, right?
Yes, sir.
So you understand, this is the same problem. This Bernoulli, student of Leibniz, and this Euler, here is a student of Bernoulli. So this Euler and Bernoulli, they developed this profile, deflection profiles of the beam, and following their name, the beam bending equation is known as Euler-Bernoulli beam equation. This is the basis. Okay, and their implementation. Okay, how? So Euler-Bernoulli developed the equation. Their solution part, how it can be solved, Lagrange is there. Who again is a student of Euler. So you see the heritage here. From Bernoulli it came to Euler, then it came to Lagrange, then there is Hamiltonian for dynamic systems, etc. etc. So these are the developments in the field of continuum mechanics. But in Newtonian mechanics, these are the laws. So that in that pathway, you won't find the development, because there is no scope as such, because it is using some quantities which is derived from a higher object. Unless you go to that object, you cannot do something more with this derived quantities. This is basically the benefit of the energy principle, radiational principle, whatever way you say it. Okay. So this is the thing, developments in radiational principle, and then now we have to talk about the computational mechanics. So here you see, continuum mechanics is good enough. We understood what is continuum mechanics. Right? The development in continuum mechanics, this is what we have discussed vis-a-vis Newtonian mechanics. The advantage of continuum mechanics we have talked. Now what happens? Continuum breaks down. Right? Continuum breaks down, what will do in that case? Right? So when continuum breaks down, still there is some mechanics. There is fracture mechanics, other things, fracture, fatigue, etc., etc. Some phenomena are there. Plasticity theory, although plasticity theory follows continuum mechanics, but whatever thing, there are further progress. This is some phenomena we observe in nature, it happens. So science cannot stop with the failure of continuum mechanics. There's to move on. So that part, okay, is basically named. There is no particular name for that area as such, because this particular development is not very old. These are all recent developments starting from 1950. So what was the driving force behind this development? It's basically the development in computational power, the computers. What was the development in computers? When it came into existence. Although development of computer has a quite old source, but actual drive came in Second World War. Okay, the Manhattan, which could develop the nuclear, and then people could really understand what is the power of computer. Previously computers were used for the navigation of ships, for the census studies, etc., etc. But really, after Second World War, people from around the globe, everyone could understand what is the power in computational machines. So from 1950s, there is so many computer companies, so many forms of computers, new generations of computers started coming. Okay. So from that point, this branches of mechanics where continuum mechanics fails or continuum breaks down, those area, fracture mechanics, etc., etc., those areas started flourishing. That's clear. So the driving force behind those sciences is the development in computational power. So that is why you will see sometimes people say computational mechanics, although this is not a very well defined terminology, right? What is meant by computational mechanics? If you give a Google search, no one will say it is like that. Is it clear? But this is how computational mechanics is contributing. So this particular terminology, what I am telling, you might not find in anywhere. This is somewhat what I have found. It's okay. So variational formulation and computational mechanics, what is there? The study of numerical. This numerical solution is always advancing, that you must understand. The numerical equation which arise in various branches of solid mechanics, finite element method implies use of computational mechanics in continuum mechanics. This is okay. So computational mechanics is a specialized area, subset of continuum. So when continuum breaks down, again the laws of continuum mechanics are valid in the two or three, whatever, in those domains continuum mechanics laws are valid, but you have to break down. Okay?
So when the continuum mechanics formula will not explain the
If it is not a continuum, say a solid body, if you go within, what you will find? There are grains.
yes.
So there is no continuum. You cannot apply the equations of those continuum mechanics in it. Okay. So a solid body, it contains many such grains. You take up a grain.
Yes, sir. In medium there are many type of fracture will be there.
No, in fracture you can say there are two different domains. Think of a solid block, which is crystalline. Crystalline structure, it has many grains.
Yes.
You go into a particular grain, take it as a continuum. You can apply the laws of continuum mechanics for that grain. So each of those grains you can analyze, you can add them up together.